All right, so what I'm going to do in this video is go through some of the concepts involving quadratic functions and how to graph them in particular. So we're going to do it by factorizing, we're going to do it by completing the square, and we're also going to get into sketching full quadratic functions in ax squared plus bx plus c. So all quadratics are going to be a parabola, as we know from last time around in year 10. The simplest one is your x squared, which is going to be located exactly at the origin and then moving up as the parabola way. Just a bit of added interest, which is the parabola comes from putting basically a flat surface through a cone, which sort of creates the name conic sections, but that is sort of external to the course, just a bit of interest. So the terminology around parabolas, there's a few things that we need to know. Some of them are obvious, some of them are less obvious. So we've got our axis of symmetry within the middle, which is basically where we can draw a mirror image on either side. We've got our x-intercept 1 and our second x-intercept. With quadratics, we don't always have two. We might have a repeated intercept or repeated root, or we might have none at all. You've also got your y-intercept, which is super important when we're graphing these. And then we've also got our vertex, which in this case is a minimum. But for example, if my parabola looked a little bit like this, that's a terrible drawing, but regardless, that would be a maximum. So depending on the direction of your parabola, you've either got a minimum or a maximum. You can't have both. So the vertex, bit of context there, we might also call that the turning point, but generally I'm going to try and refer to it as vertex because that is one of the things that we describe a form of quadratic as. So if we're sketching a graph of what I would call a relatively simple quadratic, we've got this in factorized form. The things that we need to take into account, first of all, is whether we have a coefficient at the start, and although there's not a visible one here, the coefficient, which we call a, would just be equal to 1. Now, the easiest way to determine if you're going in a positive direction, like a smiley face, or a negative direction, is just to think positive A is going to give me a smiley face, and negative A is going to give me a frowny face or a sad face. So we've determined that we've got A equals 1, which means it's going to be positive, so it's going to be a happy face. Now we need to look at the x-intercepts. And again, this is going back to null factor law, but we can also think about it as x take p and x take q, where p and q are our x-intercepts. So based on that, if we go across to our graph, we can see that our first intercept is at positive 3, and our second intercept is at positive 5. Another thing that we want to also consider is the y-intercept, and the y-intercept occurs when x is equal to 0. So we can find that really easily by saying, okay, y equals 0 take 3 times by 0 take 5. Negative 3 times negative 5 is going to give me 15. Now on my graph on the right, I don't have the space to go all the way up, but we can just imagine that it's going quite high before it contacts the y-axis. To figure out our axis of symmetry, all we have to do is basically split the difference between our two x-intercepts. This one's really easy because we've just got 3 and 5. So clearly, because it's symmetrical, it's going to be an axis of symmetry at 4. You could also plug that into the equation of 3 plus 5 divided by 2, which is 8 over 2, which is 4. But that's kind of redundant because it's really quick to do with this one in specifics. So what we're going to get here is something shaped a little bit like this. It's not a very good drawing, but that is what I'm expecting at this stage. If you can fit the y-intercept in, that is also something you should consider. And that's basically all there is to a very simple factorized quadratic. If we look at a factorized quadratic that has a squared factor, now that means that we've got a repeated root. So effectively, if we wrote this in expanded form, we would have y equals x take 2 times x take 2. So p and q would be equal to 2 and 2 respectively, but that doesn't mean that it's going to cut through the axis twice. It's just going to cut through the axis at x equals 2. So that's our x-intercept. The axis of symmetry is just going to be the exact same because 2 plus 2 divided by 2 is going to give me just 2. So let's draw that one. But before that, I'm also going to see what my y-intercept is, which is happening when x equals 0. So y equals 0 take 2 squared. So negative 2 squared gives me positive 4. So I can actually draw that in on my graph and get a bit of a better diagram there. And so we have y equals 4 as our intercept. So slightly different. The other thing I forgot to mention was that we have a positive a. So a is equal to 1, therefore that's positive. Therefore we've got our smiley face. When we get into this form, where we have effectively something in the brackets squared, so like a factor squared plus 3, that is what we call vertex form. So vertex form refers specifically to where the vertex is in our quadratic. So the form is, as you can see above, something times, let's just put little a there, equals a times x take h squared plus k. Unfortunately, they just give us random variables because they don't want to reuse them. So the vertex coordinates are at h, k. So x is equal to h, y is equal to k. If we just take a second to go back to our transformations, you might be able to identify what's going on here. So if our original function was just y equals x take 1 squared, we have vertically translated it up by 3 units. If we are just taking y equals x squared plus 3, then we have horizontally translated it across by 1 unit to the right. And that's basically how this comes about. So that's given us some pretty good information. So we know that our vertex, based on those equations, is 1, 3. Now we also want to look at A. A is just equal to 1. It's positive, so we get a smiley face. So nice and straightforward. So if we look at our graph on the right, let's go to the right by 1, and then we're going to go vertically by 3. So we're starting up here. Now, the axis of symmetry is just going to be the same as whatever our x-coordinate was. So if we just draw in a nice little line there, we could find the y-intercept as well. Again, that always happens when x equals 0. So y equals 0 take 1 squared plus 3. So we get negative 1 squared, which is 1 plus 3. So we have a y-intercept of 4. So if we go up by 4, that is our intercept. Let's draw our beautiful little diagram. Y equals 4 here. It's somewhat symmetrical by my drawing, but it should be perfectly symmetrical. And that is how we draw it in vertex form. Now, I prefer that you include this y-intercept because that shows a higher understanding, and it is what is expected of that sort of A grade. When we look at these two equations here, what we start to be able to pick up is that there is a big difference with them. And again, this goes back to transformations. Everything is going to relate back to that. Looking at our red line, we have a positive 2 at the front, and our blue line has a negative 2. So we've got a positive smiley face, a negative frowny face. If we look at this one here, we've got the same thing, +2 versus -2. Because it's got a squared factor, we know that it's going to be just touching, and we see the difference there. And finally, even with vertex form, if there is a negative coefficient at the front of our squared factor, or a positive, that is going to determine if it is smiley face or frowny face, or positive or negative. So hopefully that is super clear. If A is positive, actually let's write that somewhat different. A equals positive, we get that smiley face, compared to if A equals a negative, we are going to get that frowny face. Put little eyes on it to make it clear. So we call that concave up or concave down. We don't talk about convex, which you might have heard in some of your science or early maths. But effectively, at the end of the day, as long as you're identifying the positive A versus negative A, that's the key thing. Concave up and concave down, you can kind of gather that from the direction of your sort of infinite arrows and where they're heading. There's quite a few different things when you're trying to graph them, but if we break it down into those simpler ways of doing it, it will be much less tricky to gauge what's going on there.